Hello everyone, I hope you all are fine. So let's start our today's session. In our today's session, I have brought the new topic for you, that is the stability of completely filled and the half-filled subshells. So here I am going to tell you why the half-filled and the completely filled subshells are completely stable. So as you have to see, I have written D5. D5 is more stable than D4 if you compare with D4. If we are comparing D10 with D9, then D10 is more stable. If we compare D5 and D10, so naturally D10 will be more stable. So here I mean to say, whenever the subshell is half filled or the completely filled, in that case that will be of more stable. So here we will discuss the reason behind this. Okay, so now you have to see, I have written for you, actually there are the two reasons. One is to be of symmetrical distribution of electron and second is to be of exchange energy. So you see here, the stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their position and the energy. The number of exchange that can take place is maximum when the subshell is either half filled or the completely filled. So the overall theoretical concept explains that whenever the subshell is completely or the half filled, then the chances for exchanging position and the energy by the electron will be maximum. So here you see, here I have made some figures for you that will help you to understand that concept. Okay, now you see, the first I have made, suppose the d orbital is having 4 electrons, so that can exchange their position by in this way, that can, so there are 3 exchanges by the electron 1 that can change this position with this electron and this electron. Then 3 exchanges chances are to be there. If we will talk about with the second electron, so that can exchange their energy with the 2 times. And if we will talk about the third one electron, so that can have the capability to exchange its energy 1 time. Okay, so here are the total exchanges chances are 3 plus 2 plus 1, that is the total number of 6. Okay, let's talk about if the d orbital is having total 5 electrons. So if you will see, the 1 electron can exchanges its position 4 times, so then 4 exchanges are possible. And if we will talk about in this case second electron, then it shows the 3 exchanges. If we will talk about the third electron, it shows 2 exchanges. And if we will talk about the fourth electron, it shows the 1 exchange. So the total number of exchanges are to be there 4 plus 3 plus 2 plus 1, total we are having 10. So the total number of exchanges in case of D5 are 10, but in case of D4 the total number of exchanges are only 6. So that shows that the D5 is more stable than D4. So that is the main reason why do we call it half filled and the completely filled d orbital is more stable. Okay, so now whenever we will do the electronic configuration, so the same thing we have to follow whenever we are reaching near to the half filled and the completely filled d orbital. So as a result, the exchange energy is maximum, so the stability is also maximum, that we have to understand. Okay, and exchange energy will be maximum in case of if the orbital is half filled or the orbital is fully filled. So here I have brought the electronic configuration of the elements, those are having the atomic number 21 to 30. So let's discuss one by one. So first is scandium, its atomic number is to be of 21. So how its electronic configuration is to be done? 1s2, 2s2, 2p6, then 3s2, 3p6, and after that what orbital comes? This is of 4s2, and after that 3d comes. Then if you will count the total numbers of electrons present in previous orbitals, 6, 7, 8, 9, 10, 10 and 6, 16, 17, 18, 19, 20, 20 completed. So 1 electron we will enter in d orbital. So now for the titanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d2 is to be written in that case. Okay, now next you see in case of vanadium, it is of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d3 is to be written. Now for chromium, if we will reach up to here, 2s2, 2p6, 3s2, 3p6, 4s2, and we will get it 3d4. So when we will reach near about 3d4, then we have to convert into stable configuration. So in place of 3d4, 3d5 is to be written, and one electron will enter from s orbital to d. So it is to be written here 1. Why we have done this? Because d5 is more stable than d4. Okay, so you have to mark this chromium. This is the exceptional case of electronic configuration. Okay, let's talk about manganese. 1s2, 2s2, 2p6, 3s2, 3p6, 4s, and now 3d5 you have to write, and now the next electron will enter here 4s2. Okay, because 3d5 is stable. Now 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now you will have 3d6. Now next is to be of 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 is to be filled first, then 3d7 is to be written. Now in the next case, for the case of nickel, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8 is to be written. When we will reach on the copper, then you will observe 1s2, 2s2, 2p6, 3s2, 3p6, then what you have to write? 4s2, but we will get there 3d9. Again we are reaching to the stability, so you have to make it 3d9 to 10, and one electron will enter from S to D. Okay, and you have to mark on this copper also. This also becomes the exceptional case, which is having the atomic number 29. Let's talk about the zinc. What is to be done in that case? 1s2, 2s2, 2p6, 3s2, then 3p6, 4s2 is to be written, and 3d10. Okay, so I think you all have got how to do the electronic configuration of elements having the atomic number 21 to 30. And here two exceptional cases arises. One is of chromium and next is to be of copper, where we have to show half filled and fully filled d orbital. That's all for today.